Thank you very much. So thank you for the introduction. Thanks to the organizers for the invitation. And to all of you, welcome to the RAM session. Lance and I are going to talk about distributed discrete log and its applications for the next far too much hours. So what's a distributed discrete log? So basically, we're going to tell you about a technical tool which has found great success over almost the past decade in replacing fully homomorphic encryption in many applications and replacing it with group-based assumptions, so DDH and DCR. Now, I'll be handling the easy part. I'll basically do the DD-Log 101 course, and things are going to be very high level. We're going to make a lot of simplification assumptions, and so that we can just introduce the ideas. And when things get too serious, Lance will take over. Now, I do need to address a few things first. There is some baggage we need to address in order to understand the talk. Deep mathematics. So, okay, whenever D-log appears on screen, I mean discrete log, and DD-log means distributed discrete log. Now, everyone's caught up. And what's the plan for the next 45 minutes? So I'll start by, again, high-level description of what the problem and the tool of DD-log is. And I want to first convince you that it's useful. So I'll sketch some of the applications and see how it's useful before I even tell you formally how you build it, how you even more formally define it. And I'll keep that for the end of the talk. And then we'll roll with Lance's talk. I like to summarize this as I'll answer every question you you didn't know you had about DD-log. So what, why, where, how. What is DD-log? So, okay, let G be a cyclic group. And I promise this is the last mathematics we'll be doing for the next foreseeable future. So I just want to attract your attention to the top right of the slide, because that's an important notation we'll be using. So we'll be doing with secret shares of secrets, and mostly in the two-party setting. So say two parties, Alice and Bob, they have what I call subtractive shares of a secret. So two values x1 and x0, which when you subtract them, you get an x. And say you are in the setting where Alice and Bob don't actually have shares of x. They have g to the shares of x. How would you be able to generate shares of x, to derive shares of x from that? And this is the core problem that the distributed discrete logarithm hopes to address. And I just want to emphasize, I'm not looking for an interactive protocol. Alice has g to the x1, Bob has g to the x0, and they both have to locally apply a function and locally derive their shares from this. Now, of course, you could use the discrete logarithm to solve this problem. In most cases, it's actually as a distributed discrete log is interesting wherever you can't do as a discrete log, say in DDH hard groups. And so the way DD-log sort of relaxes the problem in order to bypass any impossibilities is to allow the parties to, the goal is still to generate shares, but it doesn't have to be the same shares that were in the exponent. They can be offset by some value that the parties don't know. Okay, so let's say we have an algorithm, like a deterministic local algorithm DD-log that converts G to the share of X into a share of X. How would you actually use this? I'm going to talk about two applications. So the first one, homomorphic secret sharing, is the oldest. And it was actually the reason why the DD-log problem was introduced. While the second application is the most recent one, it just appeared on ePrint last week, and the authors were kind enough to let me present it here today. At the core of both of these applications, you have the following problem. Let's say parties, Alice and Bob, have shares of two inputs, X and Y. And they need they want to convert this into shares of some operation on these inputs. So either additions or multiplications. Now, additions, these are all fine and easy, right? You can just locally, you have your share of x, your share of y, you sum them together, you get the share of x plus y. Multiplication is where it gets tricky and where we're going to use the distributed discrete log. And for the rest of this talk, I'm going to make the simplification assumption that g to the x is actually a secure encryption of x. Now, in reality, you'd want to replace that with an Al-Gamal encryption, but it just adds some technical, some noise to the problem, and all of the ideas can be understood with the simplification. And the way it works is, what if, let's say, I gave the parties access to g to the y, the same one. What they can do is they can take this encryption of y, raise it to the power to their share of x locally, and now what both parties have is g to the share of x times y. And now if they run their distributed discrete log, they indeed get the share of x times y. And now this is the basic idea that's going to underline roughly all of the applications. Now it gets trickier, like when Lance talks about more advanced applications, but this is the basic reason why ddlog is useful in secure computation. It allows us to avoid interaction when converting shares. Now let's go into more detail about the first application, homomorphic secret sharing. Now, at a high level, it can be seen as a secret sharing analog of fully homomorphic encryption. Instead of having parties have access to an encryption of some value x, and they want to derive an encryption of f of x, just by applying local operations, we'll do the same thing with secret sharing. So you have shares of x. How can you get shares of some function of x? And in this case, my function is a circuit, C. Now, in a bit more detail, I'm allowed, like there are two operations. I'm allowed, when I share a secret, I'm not only allowed to give you like subtractive shares, as I said, like two values that sum up to x. I'm also allowed to give you some auxiliary information, provided it doesn't trivialize the problem, provided it's much less complex than the function I'm trying to compute. And concretely, it's going to be encryptions like of the form I told you. Like it's going to be g to the x for every input. Okay, now recall we're still in the world where g to the x is a secure encryption of x. How do we actually build homomorphic secret sharing? So the first thing to note is that we don't have fully homomorphic secret sharing. The best results we have are homomorphism, which is log depth circuits, so NC1. And so I'll just ask you to trust me on this, that if your circuit is expressible as like it is a log depth circuit, then it can be expressed as what's called an RMS program, restricted multiplication straight line. And what that means is that I just have a restriction on what type of multiplications I'm allowed to do. You take two inputs, you're allowed to add them. You take any two intermediary values, you're allowed to add them. However, the only operation I'm not allowed to do is to take two intermediary computation values and multiply them together. The only multiplications I'm allowed to do is if one of the inputs to the multiplication is actually is an input to the circuit. So this is what I mean by like having input on the left input wire. Now, provided we had a circuit which is built up of these two type of gates, how do I do HSS from ddlog? So as I sketched earlier, it's exactly what I said. It's linear gates. You just add up your shares locally, you're good to go. And for multiplications, because you use the fact that always one of your inputs to your multiplication is an input to the circuit, I can assume I was given like an encryption of the input value. I never need like something g to the z, where z is like some kind of intermediary value of the system that I don't know. I don't need that because it's an RMS program. So concretely, the way the secret sharing scheme works is that I'll give you shares of your inputs, encryptions of your inputs, and that allows you to compute shares of your output of your circuit. Now, the second application is a tiny bit more involved, but follows along the same ideas. So first, perhaps, what is arithmetic garbled circuit? What is an arithmetic garbled circuit? I'll quickly remind you what it is in the Boolean case. So the high-level idea is it's a primitive that allows you to do secure computation in the following way. You take a circuit and you garble it. So that means you produce a garbled circuit, so like a circuit that hides what's you provide a garbled circuit and you provide garbled inputs. And the garbled inputs are labels. And you have to be able to garble the circuit before knowing what the inputs to the computation are going to be. Now, when the input comes along, you can retrieve the corresponding garbled inputs, so retrieve the corresponding labels to your inputs, and use them and evaluate your garbled circuits on the labels you have and produce the output of the computation. Now, the arithmetic case is a tiny bit more complicated just because, like say my field, my underlying ring is of exponential size, I can't afford to give you one label per possible value of my input. So for that reason, I need somehow to compress it, and some very smart people have figured out that the correct way to define an arithmetic garbled circuit is to instead say, okay, each label is going to be a linear combination. It's going to be a linear combination of the input, basically. So replacing my labels with just coefficients, and we construct our labels this way. So I guess the core problem in designing an arithmetic garbled circuit is, okay, say you have your labels. For each one of your inputs xi, you have such a label. How are you able to compute, so both garbler and evaluator, how are they non-interactively going to compute labels for the output of the circuit? And then going from the label, the output labels, how do they able to derive like the actual value of the computation? Now, the first thing I'm going to like restrict ourselves. I'm going to tell the garbled circuit, the garbler, to always make sure the first coefficient ai is 1. And so now you can see that one way of seeing things is that these are shares of the input x. Right? The label is known to the evaluator, and the coefficient, which is sometimes referred to as a key, is known to the garbler. And so now the problem becomes, okay, say I have two labels to like an addition or a multiplication. How do I produce the label and key to the next operation? And so again, this is where so you might think, we're done, we can just choose the same HSS trick, but not quite, because recall that the garbled circuit has to be produced before knowing the input. So in this case, it means that the garbler needs to be able to compute their share without actually knowing what the input is. And the way we discussed it previously would require the garbler to know g to the y, which means knowing y, which means knowing the input. So we need to be slightly more clever in how we do things. And I claim the following identity holds. Now, if you don't trust me, you can just check this holds, but hopefully you do trust me. And so, okay, notice the following identity. The point is, if you want shares of x times y, the term x1 times y1, that's fine. The evaluator can do it locally. The other term on the right, x0 times y0, the garbler can compute locally. What's the problem are these cross terms, x times y0 and y times x0. However, I said the garbler doesn't know what the inputs are, but he does know what his own share of the inputs are, because he chooses them. So he can just encrypt shares of the inputs instead of encrypting the inputs. And so then it all works out. Now I'll show you more concretely, like perhaps a run of the garbled circuit. Okay, so say you have the following circuit, x, y, z, and t are inputs to this circuit. What the garbler does, first of all, is to sample his own input shares. Now, in garbled circuit terms, it means sampling the coefficients, the BIs I told you about, that allow you to, as a linear combination, generate the labels. So let's start with an addition gate, because that's the easiest. Just locally, the garbler can derive their share of the addition. Now, when you get to a multiplication, the garbler is going to add an encryption of his shares to the garbled circuit. And now use this and the discrete and the dt log in order to compute shares of the product of the two inputs. And then we just continue on additions locally, and whenever you need to do a multiplication, you give out encryptions of the shares you need. And at the end of the day, like the final share they get are called the output share. And it's also going to be included in the garbled circuit in order to convert labels into the actually correct output. Now, when it comes time to evaluating this garbled circuit, assume that the evaluator has been given the linear combination corresponding to the label, meaning it's given the other share of each input. And it just uses the fact it has access to like G to the share of, so G to the garbled share in order to perform, and the DD log in order to gate by gate compute shares until they compute an output share. Then they just do they subtract output 1 from, output 0 from output 1, and you're good to go. So this is how you can do arithmetic garbled circuit with actually a pretty good rate, but Lance is going to talk about that, from the DD log. And what I like is that it's quite conceptually simple. You really, it's all about how do you do these multiplications non-interactively, and you do that using a distributed discrete log. So just to recap, I'm just going to talk about these two applications, and they share this common theme that you use DD log to do this to bypass multiplication gates. But there are two different challenges in these two applications. When you're doing homomorphic secret sharing, the main challenge is that you can't afford to give out like one encryption per multiplication gate. And this core restriction, just because I want, I want the sharing procedure to be sublinear in the circuit size. Otherwise, I could just compute the circuit and give out shares. It would be trivial. So this restriction that sharing must be much smaller than the circuit size is the core restriction. Is the core reason why I can only handle NC1. I can only handle restricted multiplication circuits and not fully homomorphic secret sharing. Now, on the arithmetic garbling side of things, we're happy with a linear rate, like a constant rate construction. However, the challenge to address is that you have to be able to generate shares and you have to compute shares without actually knowing what the inputs are. So two different challenges, but somehow DD log allows us to address both. Now, hopefully, with these two examples, you're convinced that DD log has at least some reasonable applications in secure computation, but let's say cryptography in general. And you can stay tuned for Lance's talk if you want even more applications. For now, I'll just give you a quick recap of what is known, basically what is the literature on the distributed discrete log. So I just mentioned this talk is not sponsored by Microsoft. I chose the colors sort of at random. Now, the pioneering paper is Boye, Gilboa, and Desai, breaking the circuit size barrier for secure computation under DTH. And so they were the ones to introduce both homomorphic secret sharing and the distributed discrete log problem. Now, they built the DD log, which we're going to see later in this talk, in DDH hard groups. Now, there is one limitation on the solution, however, is that it has some error in share conversion, right? So even if you give me G2 shares of X, once you apply the DD log, you have a 1 over polynomial chance that an error will appear, that after DD log, you no longer hold shares of what was in the exponent. But assuming you have you can then run some kind of interactive error correction procedure, you're usually good. Then there was a Fazio et al. Provided, they made some interesting observations about BGI's construction, and particularly they noted that it could be extended to work in DCR groups. And this is, yes. In DCR groups, however, they still had the same 1 over poly error problem, which was only going to be addressed in later works. Now we could ask, in DDH hard groups, can you get rid of this 1 over poly error? Can you achieve negligible error? And the answer is mostly no. So there are two papers that, so basically they studied the distributed discrete log problem, And they improved the original algorithm, but on the negative side, they showed that if you could completely get rid of the 1 over poly error, you could actually also solve the discrete log problem in the same group. So I'm hoping you can't do that, or most of my papers are broken. Now, I'm not going to talk too much about these lower bounds. I just want to encourage you to go and see them and note that one of the papers cited and like one of the core techniques that makes these algorithms work is called kangaroos, monopoly, and discrete logarithms. So you can always have a look. Sorry. We'll see that in just the next slide. Sorry. So it's the decisional composite residuosity assumption. I'll define what the group is, not what the assumption is. So in these magic groups, more recently, two papers proposed solutions which, for the first time, got rid of the negligible error. Got rid of the non-negligible error. So these are, I guess, like really interesting when it comes to applications. And finally, I'll also mention that there was a similar extension to an assumption based on class groups or imaginary, class groups. Okay, so in what time I have left, I will focus on the constructions in the DDH and DCR groups. Now, for DDH, the solution, parties have G to some share of some secret value. How they are going to retrieve shares of the exponent is going to be a two-step process. First, they're going to have to find some way to agree on some common group element. And from there, once they've agreed non-interactively on the same group element, they are going to somehow determine the distance from their group element to that common group element. And like by setting their shares to be the delta, they have shares of what's in the exponent. Now, perhaps visually. I'm working in a cyclic group, and like each point on this cycle is going to be a group element. And and whenever I multiply by G, I go like clockwise on the cycle. So how do you agree on some common point? Like you could, for instance, always agree, hey, let's go with like G to the 0 or some fixed point. The problem with that is that afterwards, you can't determine your distance from whatever point, like from your G to the X to the fixed point without actually solving discrete log. So the idea is going to be, let's try and make sure that the parties can always agree on a point which is very close to what their shares are. So one way to do this is to say, okay, let's use a hash function or just a random function which maps each group element to like 1 to some t, one polynomial value, say 1 to 12. And what that means is that roughly 1 in 12 elements are going to map to 0. Any point that, when hashed, maps to 0, I'm going to these are bold lines. These are special points. And now, any point, the two shares, the parties hold G to the x1 and G to the x0. If x is small enough, say it's a bit, it's either 0 or 1, that means that the two group elements that they hold must be very close. They're either the same one, or they differ only by multiplication by G, by one step. So they'll always be very close on the cycle. And in particular, assuming they're not too close to any of the bold lines, they'll always fall into the same segment between two consecutive bold lines, so two consecutive elements which, when hashed, map to 0. So the point they're going to agree on is they're going to take their shares and they're going to multiply by G until they reach a point which hashes to 0. So provided the intervals are small enough, they can do this via brute force, and like it only takes polynomial time. Right. So and like this is how you determine your distance to the special point, and then how you get your share of the exponent. Excellent. Now, when we so this solution is so I have a bit of time to tell you why. Yes, sorry. Yes. Okay. So the question was, why is it safe to assume that shares are so close to each other? Yeah. Okay. So that requires what the details I didn't go into is to what I actually mean by secret shares of, and in particular, like are these modular shares, or in this case, they are shares over Z. But still, if you assume you're doing your sharing on some much larger ring than what your actual payload is, so what X is, so for instance bits, then it still will be secure. You know, if even if you know, like so long as you're not like too far to the side of your interval, it's fine to know that your shares differ by -1. Okay, excellent. Good. So okay, so in this construction, in this dd-log algorithm, we have a trade-off to find, right? So what happens if both parties don't agree on the same point? And how could that happen? Well, it happens if, well, first of all, they don't have the same share, so like X is equal to 1, and one of the parties, and both parties do not fall into the same interval. And what that means concretely is that one of the parties must have, like G1 must fall on a point that hashes to 0, and the other one must fall just after that. So they will fall into different intervals once a brute force finds the next step. So it would be tempting to say, let's just make the intervals much larger so that this never happens only happens with negligible probability. But then the problem is that we no longer have a way to determine what your distance to the next special point that hashes to 0 is. And so this is the limitation of what you can do in like these generic DDH hard groups. And this is where DCR groups come into play. And basically, they're going to use a special algebraic property of these groups in order to get rid of the brute force step, which allows us to make larger intervals. Okay, so okay. For now, let's stay with this abstraction. Let's say you have, and I'll instantiate these groups in just a minute. Let's assume we're no longer working in like some DDH hard like cyclic group. I'm working at a group which has a very special cyclic subgroup. And what I mean by special is that it has these properties that make the discrete logarithm easy in the subgroup. Now, because H is here and the discrete log is hard in H, the discrete log is hard overall in G. And in the case of, so what I mean here by DCR group is basically Z over the multiplicative subgroup of Z over n squared Z, where n is like an RSA modulus. So n is the product of two lambda bit primes, and you do your operations modulo n squared. So say you're working in this group. I claim this group has this form, and so perhaps you can see it. But the special cyclic subgroup F is going to be the group generated by 1 plus n. Now, why is the discrete log easy in this group? Well, the first observation is that if you take 1 plus n and you raise it to some power, it's to some power x, it's going to, and you take it modulo n squared, all of the high powers of n disappear, and you're left with 1 plus n times x. So what that means is that, so n is public. So when you want to know the discrete log of an element of f, you just take it modulo n squared, and then you solve the linear equation in order to solve for x. Now there's a second type of like DCR style subgroup that's interesting, and that's like a generalization to higher order, I guess, to larger groups. And that's the groups that's like at the heart of the Damgard-Jurek crypto system. So now we're working with the multiplicative subgroup of z over n cubed z. So in this case, and I claim that my group can be, every element of the group is like r to the n to the a squared times some exponential, like to some x to some value. And I claim that my easy D log subgroup can be the group generated by x of 1. So 1 plus n squared over 2. And so basically you take the Fourier series. We don't need to go into details, but simply know that this is true, that if you look at an element of the form 1 plus n times x, you can compute the discrete log as this operation. So we have these two crypto systems, and how do I actually solve the DD log problem in these groups? So what I showed you before was like in the special cyclic subgroup, how do I perform a discrete log? Now, how do I perform the overall distributed discrete log? So as before, we have the two-step process. First, we agree on some common point, and secondly, we find our distance to this special point. So the special point, and this is going to be common to both constructions, is actually, it turns out that like if you take your shares and you take them modulo n, you're actually going to always find the same value. This is the first part of the algebraic structure of these groups, which make finding a point much easier than in the DDH case. And so the observation is simply that if you take 1 plus n to the x and you take it modulo n, all of the powers of n disappear, so you're only left with 1. And what that means, because recall that G1 divided by G0 must be equal to 1 plus n to the x, is that these two shares are congruent modulo n. Okay, so parties holding G1 and G0 apply modulo operations. Now they have the same point. How do you then determine your distance? Choose this point. And like taking the log of G1 over h, or is the same as taking the log of G1 minus the log of h. And so like these two shares are indeed going to cancel out. Or rather, they're going to sum up to x. And so the core claim here is that if you take your share and you divide it by h, you are going to fall within the special subgroup for which I claimed the discrete log is easy. And from there, once you have that, you can just apply the discrete log and you can indeed recover the exponent. So sorry, I'm not going to go into the details of like why that is. So basically, if you write it down, I mean, I would just recommend looking at the paper, but there's a few lines of that explains why you're falling into this group. Now in the Damgard-Jurek analog, it's almost exactly the same. Again, if you take your shares modulo n, you get the same point. Because since x of x is congruent to 1 modulo n, you get what you want. Now the second stage is going to be the same thing. I claim that if you take your share divided by the common point h, you are going to fall again in the easy subgroup, and the discrete log easy subgroup, and this discrete log easy subgroup is the one generated by x of 1. And really the reason why, so okay, let's assume, well, yeah, let's perhaps not go into the details of why we fall into this easy subgroup, but it can be shown. Okay. So perhaps just to summarize what, this is intro to the DT log, what we've gone over in this intro to DT log. It's a deterministic algorithm, completely run locally, non-interactive, which allows parties to convert group elements of the form G to some share of X and convert this into shares of X, fresh shares. Now, and this allows us to bypass discrete log-based impossibilities in subgroups. Once you have this tool, there's a core trick in all of the applications is that you can take shares of X and shares of Y, and provided you're given some kind of like encryption of discrete log-based encryption of one of the two inputs, you are able to non-interactively generate shares of the product of X and Y. And if you want to open up the hood of how do you actually solve this distributed discrete log problem in these groups, two-step process. First, you find some point which is very close to your original shares, and then you find your distance, the delta between your share and the next one. And that sums up what I want you to walk away with, and what really you need to know in order to be prepared for the next talk. And I'll just make a prediction that later we'll see the slide show up. Thank you very much.